my channel of Material Science and Engineering, you can call it as. I am Professor Dr. Sandeep Ohol. Today we are going to learn something about the composite materials. Basically, if you see the definition of the composite material, as name itself indicates, composites are nothing but we are going to add two different materials in one single material so that we will get the benefit of both the materials. In composite material, for example, in this building you are sitting, in this room you are sitting, here itself there is a composite material example is there, that is nothing but this slab and whatever the columns of this building are nothing but the good example of the composite materials. How you can say that? Because in column, if you see the material inside that, there are the steel rods, and along with that there is a granules, there is some particles and some binding material is there, that we call it as a concrete material. So if you see the concrete material, if you take a block of the concrete, its compressive strength is good, and if you take the steel material inside that, its tensile strength is good. That means we are going to have tensile strength as well as compressive strength in one single material when we are adding them together for the construction purpose. Another example of composite you may have in day-to-day life, we face tires, vehicle tires. Now there is some plastic material inside that, and in that plastic material there is again steel wires are there in the tires. So tires is also a good example of composite material again. So basically composite materials is a vast topic. If you see, it is very vast topic. Tremendous research and development is going on in that particular sector, because nowadays automobile companies are running behind to reduce the weight of the vehicle and to improve the fuel economy of the vehicle. So for that purpose, this particular conventional, you might have seen that nowadays, in old days we have seen the engine blocks made from the cast iron. After that we have also seen the engine blocks made from the aluminum material, and nowadays there is a research going on that engine block material may be replaced by the composite material or again a lightweight material. Are we going to compromise on the properties when we are losing the weight of the material? So the answer for that is no. We are not going to compromise, rather we are improving the properties. So composite material will give you the combination of two materials properties, and that properties may be different from the constituent material properties, or it may be improved version might be there in that case. Okay, so if you see here some examples I have listed. Wood is there, that is cellulose fibers bound by the lignin matrix. Basically in composite material, two terms are very important. One is called as matrix phase, that is also called as primary phase, and the second one is called as secondary phase. Primary phase or matrix phase is the base of that particular composite material. Likewise, this cement concrete is the base of this slab, and in that there are the secondary phase, that steel rods are acting as a secondary phase. Okay. So in composite, these two parameters are very much important, that is matrix phase and secondary phase. Matrix is the parent phase present in that, and secondary phase is added to improve the properties of the matrix phase or base phase. Okay. So here if you see wood, there is a cellulose fibers which are bound by the lignin matrix. Lignin acting as a matrix and cellulose fibers are acting as a secondary phase, which are improving the strength of that particular wood. Then there is a granite is also there, granular composite of quartz, feldspar and mica. Then concrete, as I have just now told you, it is a particular composite of aggregate, that is limestone or granite, sand, cement and water. So cement is acting as a binding agent. Cement is binding the particulate or that sand particles together, so that overall strength after the solidification or after drying of that particular one, you may see that it is becoming very hard, and the material which is very hard is good in compressive strength, as we have already learned in the previous lectures. Plywood is there, then fiberglass is there. Fiberglass is a very well-known example of the composite material. Fiberglass glass. Glass is the parent. Plastic matrix is going to be reinforced with the glass fibers. Then ceramics are there, ceramics plus metal composites. Then fibrous composites materials are there, variety of fibers, glass, Kevlar, graphite, nylon. These are the fiber materials. That means these are the secondary phase materials. These materials we are going to embed it with other material which will be acting as a matrix phase. Okay. So here if you see the diagram, this is my fiber phase. This is my fiber phase which may be in the form of fibers. These fibers may be of different size. Fibers may be in the form of particulate particles like cement particles or granules in the cement. Then this is your matrix phase. When we are adding to this will have some certain properties, this will have certain properties, but when we are adding both together, we will get the third material that is called as composite, which will be having some fiber reinforced composite, which will be having some distinguished properties as compared to these two materials. Okay, I hope you guys are getting. Basic fundamental, I have understood the basic fundamental of composite material. There are two phases, one is primary, another is secondary. Secondary phase is going to be added, secondary phase is going to be embedded in the primary phase, and after that, after combination of these two, we will get the third material, that is nothing but the composite material. Okay. These are some examples. If we say the classification of the composite materials, they are classified into three broad categories like particle reinforced, then fiber reinforced, and structural composite. The best example of structural composite is laminates. You might have seen that various laminar structure or plywoods, one above the other, the layers of the wood material are there in the plywoods, or you might have seen some layers of any material one above the other, that is nothing but the laminates. So here in a particle reinforced, you can have large particle size. Example may be cement concrete. It is a large particle are there, and they are bind together with the help of sand, with the help of cement and water. So large particle and dispersed strengthened particles are nothing but the fiberglass, where fiberglass is reinforced with the plastic to get the composite material. Then fiber reinforced. So particle case में दो चीजें हैं, एक large particles and then dispersion strengthened particles. Then fiber reinforcement continuous, in that again align, and discontinuous, in that again short. In the short again align and randomly. Now here in the next figure you might be understood what is the meaning of this. Fiber means a kind of thread, for example. Fiber means a kind of thread. Okay, or you can call it as a Maggie thread. Okay, it is reinforced in some material to improve the properties. So here continuous means align, if they are following certain pattern of addition. एक ही direction में. Continuous align means that fibers are aligned in certain direction. Okay, and short means जब आप मैगी बनाते हो तो उसको वो पैकेट को मोड़ के अगर डालते हो, that long Maggi threads are becoming short. That means we are breaking that threads. Okay, so that is nothing but the short fibers, and short is that is also if the addition of the short discontinuous fibers is following certain order, following certain alignment, then they are called as aligned fibers. And if they are randomly oriented, now I have one question to all of you. Which one give me the uniform properties in the material? As far as composite is concerned, whether aligned discontinuous short fiber will give me the good properties, or good rather uniform properties in the material, or randomly oriented will give me the uniform properties in the material. You can talk loudly so that it will get recorded. Right? Align. Okay. You mean to say that if this is a composite, this is a matrix phase, and I am adding the fibers in this direction, then properties may also may be aligned in the direction of fibers, na? Then what about the opposite direction then? If I have aligned the fibers in this direction, okay, I may get the properties, very good properties, in the direction of alignment of the fibers. Okay? What about the other direction? What I am asking you? I am asking you about the uniform properties in the material, or in that composite material. You may not getting my question first. क्या पूछ रहा हूँ मैं? I want as a material, I want uniform properties, ना? I can't say that in this direction properties are good, in other direction they are not good. I can't say like that as a whole. But for that I have to add the random particles which will give me the uniform properties in the material, because they are not aligned in any one direction, they are aligned in every direction, all direction. One particle may get aligned in this direction, one may get in this direction, one may this. That means in all 360 degree I can have a particle orientation or a fibers orientation, and that's why my properties will be uniform in all the aspect as far as this particular material is concerned. So as far as the design engineer is concerned, when you are going to design certain composite material, and again you have to add the fibers into that, you have to always thought of this particular randomly oriented fibers again in the form of particles, again in the form of short fibers, so that the uniformity in the properties will be there as far as that whole composite material is concerned. Okay, and the next one is structural laminates is there and sandwich panels are there. So I may have a question on this. Define composite materials. Give the classification with some examples. Define composite material. Give the classification of the composite material with some suitable examples. So example आप यहाँ से दे सकते हो. You can have composite material example like this: wood, granite, concrete, plywood, fiberglass, cement, all that. Then this, if you draw this chart, as far as classification is concerned, it's okay. This question may be there for 5 marks because this is unit number 5. Distribution of the questions will be ABC 5, 6, 6. Unit will be for 17 marks. So this question might be there for 5 marks. The next. Now, as I told you, there are two phases in the composite material. One is primary phase, which forms the matrix within which the secondary phase is going to be embedded. So this is your primary phase in which the secondary phase is going to be embedded. Secondary phase is going to be embedded to get the composite material. I am talking in general now, but by the time we will talk in detail as well with certain examples. So primary phase is nothing but the matrix phase, which is used or in which the secondary phase is going to be embedded to form the composite material. Secondary phase, this is the embedded phase. That's why the name is secondary phase. This is the embedded phase. It is also sometimes it is also called as reinforcing agent, because we are enforcing that particular phase in the primary phase. So it is also named as reinforcing agent, because it is usually served to strengthen the composite material. That means if I want to strengthen this particular material, if I want to have the more properties, strength or whatever properties you are looking for, if I add this particular secondary phase into this, as a whole, as a composite material, I am getting improved properties in this particular one. So that's why secondary phase is always going to be added for the improvement in the mechanical properties point of view, like strength and hardness. Okay, or toughness and ductility. You can, or rather toughness, not ductility actually. So composite secondary phase is a phase which is going to be embedded into the primary phase, and the main purpose of adding secondary phase is to improve the properties of the base material. As when the material or when the primary and secondary phases are going to be added, then we will get the final composite material, in which we are going to get this particular properties improvement as compared to this, or as compared to the separate materials if we consider. I hope you guys are getting. This is very, very simple. Reinforcing phase may be in the form of fibers, like in the previous slide I have shown you. It may be in the form of fibers, it may be in the form of particles like cement, concrete, or it may have some various other geometries based upon the requirement of the properties. It may have some various geometries as well. Matrix is continuous. You can see that matrix is continuous. There is no break in the matrix phase. It is continuous phase. And dispersed phase or secondary phase is going to be discontinuous or surrounded by the matrix phase. So you can see that always secondary phase in a composite material, always secondary phase is going to be surrounded by the primary phase. Okay? Shall I proceed? Is it okay? And what it serves actually. What are the functions of the matrix phase that has been listed over here? Nearly all composite material consists of matrix. Without matrix phase, there is no composite, quite obvious. Because that is the primary phase which we should have to form the composite material. So for that purpose, this is a matrix phase, is also called as primary phase, forms the matrix within which the secondary phase is going to be embedded. That means secondary phase we are going to insert. Then it binds the fibers. All the fibers which we are adding into the matrix phase, they are going to be kept together. They are going to be bound together with the help of this matrix phase. So for example, in a concrete example, that particles or particulate particles, like, so for example, in concrete material, that particulate particles are going to be bound together with the help of cement. So in that case, cement will become your matrix phase. Like in the example of tires, that steel wires are kept together, bound together by the plastic material, rubber material, which is going to be used for producing the tires. So that is your matrix phase. Whenever you are going to apply the stress for the deformation purpose on the composite material, listen to me very carefully. When you are going to apply the force on a composite material, then that force first will be given to the fibers which are there inside that particular composite material, and that force is going to be equally distributed on all the fibers present in that particular matrix phase or present in that particular composite material. So applied stress is transmitted and distributed to the fibers. So whatever the deformation you are doing in case of composite materials, whenever you are applying the force for deformation of that particular one, that force is first transmitted through the matrix phase to the fiber phase, and from fiber phase to another fiber present in that. So likewise the transformation of stress is going to be happen into that particular one. Okay. Then matrix protects individual fiber from the surface damage. That means whatever the fiber phase is there, that is inside the matrix phase. It is not going to be there on the surface or superficial on the surface. It is inside that. That means whatever the damage is going to happen, it will happen first to the matrix phase. Isn't it? जो भी damage होगा during operation, during applications, whatever the damage might be there, whatever damage may be there inside that particular one, that damage first happens with the matrix phase. After that only it may go to the fiber phase. But damage to the fiber phase is not directly happening as far as these composite materials are concerned. Then prevents propagation of a brittle crack from fiber to fiber. अभी matrix phase है, okay. In the matrix phase, if certain crack is there, that crack may go propagate to up to one particular fiber or one particular fiber or segment of the fiber. From that fiber, it may not get transferred or it may not get propagated to the another fiber. That means propagation of the crack during the through that particular composite material is also becoming difficult, because that crack is not propagating from fiber to fiber. It is might be propagating from matrix to one or second fiber, but not all the fibers in the present in that particular composite material. I hope you guys are getting what I am talking about. Matrix and fiber, समझ में आ गया? First thing, okay. This classroom you may take it as a matrix phase, and you guys are nothing but the fibers. As simple as it is. As simple as it is. So crack propagation also become difficult. Okay. Then only metals and thermoplastics and thermosets are used as a matrix phase. Metals, that means brittle, can we use the brittle material as a matrix phase? No, because it may get breakdown over the period of time due to the application of various stresses and all that. That brittle material may break down at any time. So for that purpose, whatever the metals are there, non-metals are also not considered. Whatever metals are there, thermoplastic materials are there, thermoset materials are there, they are going to be considered as a matrix phase. Then matrix phase is ductile in nature, quite obvious, it is ductile, that's why it is holding all the fibers together and just transferring the stress from fiber to fiber inside that particular matrix. It will have high bonding strength, quite obvious. Cement is having high bonding strength, it will bind together all the particulate one, and once it gets hard, you may see that it becomes more than hard like anything. So that's why it is binding strength is also good, and they are also having high corrosion resistance. So these are the nothing but the properties, or the what you can call it as the properties of the matrix phase. Okay, and based upon that matrix phase, Composites are again classified as polymer matrix composite, ceramic matrix composite, metal matrix composite, PMCs, CMCs and MMCs. Okay. On this you may have a question that discuss the properties of matrix phase in the composite material. Discuss the properties of matrix phase in the composite material. Then the next phase is that is reinforcing phase or secondary phase. The role of reinforcement in composite material is primarily to add mechanical properties to the material such as strength and stiffness. We are going to improve the strength of that particular material and we are also going to improve the stiffness of that particular material. Stiffness is nothing but resistance to the elastic deformation. Okay. Resistance to the elastic deformation, that is nothing but the stiffness. So basically the role of reinforcement or secondary phase is to improve the properties of the matrix phase. For example, here it is mentioned that strength and stiffness is going to be improved, but based upon the required properties of the material, we are going to add the required necessary reinforcing agent or secondary phase to the primary phase or matrix phase, and based upon that reinforcement, based upon that addition, we are going to improve the properties. So for example, they are talking about strength and stiffness can be improved by introducing the secondary phase into the matrix phase as far as composite materials are concerned. Now reinforcement basically comes in three types. You can see that particulate, that means like this kind of particulate particles are there which are there in the matrix phase. Then you can have a discontinuous fibers. This is short fibers and discontinuous fibers, and continuous fibers like this. These are the continuous fibers oriented in different directions. So if I put all them together, it becomes laminate. If I put all these four together, it becomes laminate, and it may also become sandwich kind of thing. Okay. So basically, secondary phase comes into three different categories, like particulate one, like this short fiber, very short fibers, then discontinuous fibers and continuous fibers. Now when we are talking about in the last lecture also we have talked about the nanomaterials, and in that lecture I have told you that when we are reducing the dimensions of the material, that means we are improving the properties of the material. In the last class also we have discussed about the fine grained material, why they are strong, tougher and better than the coarse grained material. That is only due to the reduction in the size, and that's why the technology is going into the nanotechnology. So that's why more research is happening in that particular field also. So here also, if you see the continuous fibers, as compared to the continuous fibers and the particular short fibers, this material will give better strength than this particular continuous, because here the length to diameter ratio of that particular, if the fiber is cylindrical, in that case, if the length to diameter ratio is reduced, we will get more properties in this one. Okay. Reinforcement become fibers when one dimension becomes long compared to the other one. Now what dimension these are talking about? Only length and diameter. Okay. So what they are reinforcement fiber ka banti hai. When the reinforcement we are going to consider as a fiber, when one dimension is longer than the second dimension. Here we can talk about the length as one dimension, and we can talk about the diameter of that fiber as a second dimension. So one dimension is long compared to the second dimension. In that case, that reinforcement material or reinforcement agent becomes fiber. So here you can also have a definition of fibers. Fiber can be defined as the fiber reinforcing agent which is having one dimension more than the second dimension, like that. Then discontinuous reinforcement like chopped fibers or milled fibers vary in length from few millimeters to few centimeters. So whatever the discontinuous fibers, what is the maximum length of that? Discontinuous fibers are varying from millimeters to centimeters, not more than that. Otherwise they can be called as a continuous fibers or long fibers. Okay? Okay? Understood? Then here are some classification. Metal matrix composite, mixture of ceramic and metal such as cemented carbides and other ceramics. Ceramic plus metal, met for metal, cer for ceramics. Then ceramic matrix composite like Al2O3 is there, and SiC, that means alumina and silicon carbide, is that these two fibers, these Al2O3 and SiC, that means these are the two matrix phases. When we are going to embed them with the help of fibers, will improve the properties, especially in high temperature applications. So I have also discussed this one. When we are talking about the pure aluminum, it may be soft or it may have a low melting point. But when we are talking about Al2O3, aluminum oxide, it will be very strong, it will be very hard, as well as it will be having very high melting point. So if I want to improve the high temperature properties of this particular material, I can add in this Al2O3 or SiC silicon carbide, I can add the secondary phase as a fiber material, phase into that, so that their high temperature properties are going to be improved. That means applications for high temperature are more suitable when we are going to add fiber material secondary phase into Al2O3 or SiC as a composite material. As only Al2O3, it may have low properties, but when we are adding them with certain nanomaterials into that as a secondary phase, then their properties are drastically going to enhance. Polymer matrix composite, PMCs, that is thermosetting resins, are widely used in PMCs. So you can see the examples also listed over here: epoxies and polyesters with fiber reinforcement, and phenolics with powder reinforcement. Now the first type of metal matrix composite, we are going to talk about in general information of the MMCs. Then we are going to talk about the properties of that MMCs, some examples, some applications. Okay, in these particular terms we are going to learn this one. So MMCs are nothing but these are metal matrix composite. That means matrix phase is metal and it is going to be reinforced by the other phase. Matrix phase will be metal, it is going to be reinforced by the other phase. Provides the bulk form of the part of the product. That means if you consider the composite material in a whole, it will be a bulk. That means metal will have more proportion as compared to the secondary phase. In MMCs, metal may have more proportion. If you compare 80% metal and 20% secondary phase might be there. So bulk part of this MMCs is going to be considered, or is going to be made up of metallic material. Then holds the embedded phase in place. Again, as metal is there, it will not allow to move any fiber phase or secondary phase or reinforced phase. It will stay at its own position. Once it has been added into that, then there may not be a further movement when the addition is done and when the composite material is going to be, or MMC is going to be formed. Shares the load with the secondary phase. Whatever the load we are going to apply, it will be transmitted to the fiber phase. Fiber to fiber transmission will be there, and in the end, where there is a boundaries of that particular composite material will be there, or matrix phase boundaries will be there. At that particular point, your stress transformation or whatever the load you are given to that particular one, that can be transferred. What are the reinforcing phases in that? If you see the particles of the ceramics can be considered as a reinforcing agent into that, or secondary phase into this. MMCs are common. Based upon that, MMCs are called as ceramics. That when we are using ceramic particles as a secondary phase, then it becomes ceramic, that is ceramic metal matrix composites. If we are having a fibers of various materials, we can add other materials as well. We can have ceramic fibers, we can have metal fibers, we can have carbon fibers, or we may have a boron fibers as well. So when we are adding these fibers into that particular one, based upon that particular fiber phase, it is going to be considered as a, based upon that you can give the name to that particular MMC. Like हमने यहाँ पे ceramic particle add किया, so it is considered as ceramic. If you are adding some carbon fibers or boron fibers, that can be considered. Based upon that, we can give the name to that. So what are the common metal matrix phases are there, or element which can be used as a metal matrix phase are aluminium, magnesium, iron, copper and nickel. These elements or these metals can be considered as a matrix phase in MMCs. These metals can be considered as a matrix phase in MMCs. Different metal or another material such as ceramic or organic compound can also be considered. यहाँ पे you can see that example is aluminum SiC, that is silicon carbide, or aluminum Al2O3, that is aluminum oxide. What are the properties of this particular metal matrix composite? They are having high strength, high stiffness, dimensional stability, that means there is no dimensional changes once your composite material is formed. Composite material बनने के बाद there will be no dimensional changes. So dimensional stability is there, and we can have a high temperature applications. That means it will maintain its strength, it will maintain its hardness at high working temperature as well. For example, if the working temperature is around 600-700 degrees Celsius, still this kind of composite materials are going to maintain their properties. Then they are also going to have a good toughness as well. So on this, just explain metal matrix composite, which should explain metal matrix composite with suitable examples. Till now you might have heard this word before as well, but I hope this lecture will clarify all the basic concepts in composite materials, fundamentals of the composite materials. So how they are going to be made? MMCs. MMCs are made by reinforcing the material into the matrix phase again. Reinforcement surface can be coated to prevent the chemical reaction with the matrix. That means whatever the fiber you are going to add into the matrix phase, whatever the secondary phase you are going to add into the matrix phase, for some applications or for some MMCs, the reinforced phase is going to be coated. That means we cannot directly add the reinforced phase as it is. We have to before we have to coat it before the addition to the matrix phase. Example is given over here. Carbon fibers are commonly used in aluminum oxide or aluminum matrix. Okay, carbon fiber is taken as a secondary phase, and it is generally going to be added in the matrix phase of aluminum. So while addition or while synthesis of this particular composite material showing low density and high strength. Okay, so whenever there is a point of lightweight material, but at the same time strength should be good, strength should be high. Without compromising the strength of the material, we are going to load down the weight of the material or density of the material. In that case, we can thought of this kind of composite material in which we are going to add carbon fibers into the into the aluminum matrix. So strength of the aluminum is already lightweight material, and when we are adding carbon fiber to that, it will improve the strength. That means we are not adding the weight to that particular one, and this is now required as far as design of automobile chassis and everything is concerned, to have the benefit of fuel economy and all that. So for that purpose, again, when we are adding these carbon fibers to the aluminum matrix, what is happening, that this carbon is going to react with the aluminum to form Al4C3 compound. Carbon will act with the, if carbon fibers are added without coating, उसको आपने कोटिंग नहीं किया और उसको आपने डायरेक्टली एल्यूमिनियम मैट्रिक्स में ऐड किया, so कार्बन क्या करेगा, कार्बन will react with the aluminum and forms this Al4C3 compound, and this Al4C3 is a brittle and water soluble compound. मतलब वो without कोटिंग वाला कंपोजिट मटेरियल आपने पानी में डाला, it may get soluble, okay, it may get dissolved into that water, because why, this compound is going to be formed, or it may get brittle. That means we are going to compromise on the strength or toughness of the material or ductility of the material. So that is not expected. So to avoid the formation of this Al4C3, to prevent this reaction, the carbon fibers are coated with nickel or titanium boride. See how complicated process is this. So only addition of carbon fiber to aluminum will not serve my purpose, rather it will destroy that particular composite material. So to get rid of that, to solve that particular problem, before addition of carbon fibers to the aluminum matrix, we are going to coat that particular carbon fibers with nickel or titanium boride, so that it will not come in direct contact with the aluminum matrix. कोटिंग किया है तो कार्बन एल्यूमिनियम के कांटेक्ट में आएगा क्या? नहीं आएगा. वो कांटेक्ट में नहीं आया तो ये फॉर्म नहीं होगा. ये फॉर्म नहीं हुआ तो this problem are getting sorted out. Brittleness and solubility in the water will get sorted out when we are adding the carbon fibers coated with this nickel or borides or titanium boride. Okay, so this is also equally important as far as MMCs are concerned, because many times we need to add, when we are going to add them as it is, then this kind of problems might be there, that brittleness and water solubility might be there. But to avoid that or to resolve that particular one, we can add carbon fibers coated with nickel and titanium boride. Here are some types of MMCs. You can see that particle reinforced MMCs, dispersed particles like silicon carbide or Al2O3 improve the strength and wear resistance. Wear resistance, that means over the period of time, whatever the wearing out of the material is there, that is going to be avoided, because SiC, silicon carbide or Al2O3, they are very strong or hard particles. Likewise, I have also discussed this with you guys. In polishing purpose, we are going to add that alumina particles for the fine polishing one. So that particles are very hard. So that due to that reason, the strength is going to be improved, and at the same time, wear resistance of that particular composite material is going to be improved. Then some fiber reinforced MMCs are there. There are continuous or discontinuous fibers. Basically, carbon fibers or boron fibers are used in this to enhance the tensile strength and toughness. So when we are using fibers, in the form of fibers, when we are putting that secondary phase into that matrix phase, then the tensile strength is going to be improved, stiffness is going to be improved, that is resistance to the elastic deformation is also going to be improved. Laminates MMCs, like layered structure, improves the impact resistance, and some nano composite materials are there, that is nanoparticles as reinforcement improvement. Nanoparticles as reinforcement improves the mechanical and thermal properties. So now here you can see that this is a particle reinforced fiber material, that is discrete particulate reinforcement. This is discrete short and random reinforcement, you can call it as. This is continuous fiber, and that is again aligned reinforcement. And here you can have a laminate or plate kind of reinforcement, that is nothing but the laminate. So here yellow one is nothing but the reinforcement and blue one is nothing but the matrix phase. So by this way we can improve the or we can prepare the composite material or MMCs by this way. There are the properties: high strength to weight ratio, improve wear resistance, thermal conductivity, corrosion resistance, and tailored properties. Tailoring means what? We can customize the properties. If we have a knowledge about the reinforcement of the material, if we have a knowledge about the type of material which can be used as a reinforcing agent, if we have a knowledge about the matrix phase, then we can tailor the properties or we can customize the properties as per our requirement. So that is tailoring of the properties also possible, customizable by altering the reinforcement type, size and volume fraction. Here are some applications of MMCs: aerospace, automotive, defense, electronics and sports equipment. I have just mentioned the general properties of the or applications of these MMCs. In aerospace, you can have structural component like engine parts and heat shields. Then in automotive, you can have brake disc or drive shafts or engine components and enhance wear resistance. In defense, we can have lightweight armor and high strength structural components. In electronics, we can have heat sinks, like I have used in my research work as well, heat sinks and thermal management of devices. And sports equipment like bicycle frames, golf clubs, and some high performance gears can also be made from the MMCs. Here are the advantages: increase mechanical strength and stiffness, enhance thermal stability and conductivity, customizable for specific application, and improve fatigue and creep resistance. We have already talked about the fatigue and creep resistance. So I hope you guys know what exactly the meaning of fatigue and creep resistance. What are the challenges in front of MMCs? What are the challenges while using the MMCs? The manufacturing cost is high. Because if you want to produce Al2O3, that is again taking time and also the cost is also high. Then there are complex fabrication processes there. Addition of laminates, fibers, long fibers, aligned fibers, then randomly aligned, then or aligned in one direction. That kind of reinforcement becomes difficult sometimes. Difficulty in machining and shaping, because for example Al2O3 and SiC, they are very hard enough. So machining becomes difficult. That means forming the different shapes or cutting out that composite material become difficult. And some potential issues with reinforcement matrix bonding. Some bonding issue with the matrix and reinforcement phase. Bonding issues are also there in this particular one. Again, Question may be, what are the different types of MNCs? Here are 4 MNCs are there. You can draw this diagram for that as well. Then discuss the properties and applications of MNCs. This may be one question. Discuss the properties and application of MNCs. And the last question on this, what are the advantages and disadvantages of MNCs? This kind of question you may have. I think it's time. We'll stop over here.